So today I'm going to speak about a novel approach to derive the black hole entropy, or black holes in 4 and higher dimensions. And most of you will be able to understand everything because the calculus necessary to show these derivations are basically straightforward. So any one of you who has taken basic calculus will be able to understand what I'm going to talk today. So let me proceed. Okay, so I'm going to start at the beginning to explain what the Sinh-G method is, which is essentially running the Einstein's equations backwards. Then I will talk about the Schwarzschild metric. And then what I'm going to do is I'm going to have a simple modification of the Schwarzschild metric, which is actually, in a certain way, many will think it's absolutely trivial, this modification of the Schwarzschild metric, but it has profound consequences. So you will see how a simple twinkering of a mathematical solution can have profound physical implications. Then I'm going to show, that the Euclidean Einstein-Hilbert action is going to give you the black hole entropy in 4 space-time dimensions, and I will extend the result to the black hole entropy in higher dimensions than 4, and then I will go to one of the main points of the whole talk, is how one is going to have a mass density configuration and an anisotropic pressure configuration of point masses. So the issue of anisotropy is essential. You will see why. Then I will talk a little bit about the weak and strong energy conditions, that when you impose these weak and strong energy conditions to your space-time, these conditions are going to single out the space-time dimension that you and I perceive since we are born. We perceive 3 special dimensions and 1 temporal dimension. So we experience a world of 4 space-time dimensions. So I will show how from these weak and strong energy conditions you can show that they single out d equals 4 from all the other space-time dimensions. So this is probably, in my opinion, the most significant result. Then, if I have time, I'll talk a little bit about what primordial black holes are. These are black holes that are postulated to have been created at the beginning of the universe, when we didn't have any stars, when we didn't have any galaxies. So therefore, the notion of gravitational collapse of a star would not make any sense, because there are no stars to begin with. So I'll talk a little bit about that. And then, very briefly, I'll show how to generalize the result to the Reissner-Nordstrom Black Hole Entropy, which is a black hole that has mass and charge. And then the Kerr-Newman black hole is a black hole that has charge, mass, and angular momentum. Okay, so I'm going to concentrate first on the Schwarzschild solution. Okay, so let me just proceed. Okay, what is the Sinh-G method? Okay, and before I begin throughout this talk, for the next 1 hour, I'm going to use these units where the reduced Planck constant, the speed of light, and the Boltzmann constant is equal to 1. So I'm going to be working with this system of units. Okay, and then so what happens in general? When you study relativity, you usually start with an action that involves essentially 2 terms. One of them is the gravitational action that involves the curvature of space-time, and another action that involves the matter terms, or you can also include the electromagnetic field. So essentially you have a combined action that involves a gravity and matter term, and when you perform a variation of the action, you want to minimize this action, and when you set it to 0, you derive the Einstein field equations. And so on the left-hand side of the Einstein field equations, you're going to have what you call the Einstein tensor, which has the Ricci tensor over here. Here you have the metric, here the scalar curvature, and in the right-hand side you have the matter contribution. So Einstein postulated his field equations But later on, it was Hilbert who postulated an action principle that gave birth to the Einstein's equations when you perform a variation of the action. So here on the right-hand side, you have is the stress energy tensor that is given by a variation of your matter Lagrangian with respect to the metric. Here, this is the square root of the absolute value of the determinant. So this is like a measure term. And the gravitational action of gravity is given in 4 dimensions. It's given, again, you have the scalar curvature. Here, I write the absolute value of the determinant of the metric as minus g, because after all, the determinant of the metric tends to be negative definite. So if you want to extract the absolute value, you include a minus sign in front. But in reality, if you want to be rigorous, just write the square root of the absolute value of the determinant of the metric. So this is what contributes to the measure in your action. Here in the bottom, you have the Newtonian, the gravitational constant. Okay, so this is the action of gravity, and so essentially, when you do a variation, you end up with the Einstein field equations. So what do you do in general relativity? So what you do is you postulate a stress energy tensor. So you try to solve these differential equations. Because remember, on the left-hand side, you're going to have a system of partial, non-linear differential equations, which are in general very difficult to solve. And these are differential equations of second order. And then in the right-hand side, you have the matter distribution. Now, the Singh method is something that is something which is the opposite picture of the Einstein field equations. In the Singh trick, what we're going to do is we're going to run the Einstein field equations backwards. So in other words, we're going to postulate a metric. Once we know the metric, we are able to determine what the connection is and the curvature by taking ordinary derivatives. And then we're going to determine what the term in the right-hand side is. So we're doing it backwards. So we postulate a metric, we evaluate the Ricci tensor and the scalar curvature by taking ordinary derivatives, and then the result we get, we equate it, so the result we get is going to tell us what the stress energy tensor is. So we're doing it backwards. And you'll see in a minute why this is very useful. Okay? So again, the Singh trick is just running the Einstein field equations backwards, meaning that firstly, we postulate a metric, and then afterwards, we determine the stress energy tensor in the right-hand side associated with that metric. Okay, is this clear? Okay, so let's proceed. Yeah. So have any one of you taken general relativity? By anyone? But you have heard of the Schwarzschild metric? You see, in 1916, Schwarzschild is the first person who found solutions to the Einstein field equations. Actually, he found what he calls static, spherically symmetric solutions to the Einstein field equations. But actually, the solutions that he found are very, very special because what he did, he set 0 in the right-hand side. So this is what you call the vacuum field equations when there is no matter at all. So he wanted to find solutions to the field equations in the simplest case where he assumed a spherical symmetry and where the metric does not depend on time. And you see, the solution that Schwarzschild found is not the solution that all of you are going to read in your textbooks for the past 100 years. This solution that you find in all textbooks was actually given by Hilbert, not by Schwarzschild. But for historical reasons, everybody calls it the Schwarzschild solution. The solution that Schwarzschild found is the same as the Hilbert solution up to a diffeomorphism. Remember, the Einstein field equations have a symmetry which are invariant under coordinate transformations. So the solution that Schwarzschild found is the Hilbert solution up to a diffeomorphism. But for historical reasons, everybody calls this the Schwarzschild solution. So here, this is the time component of the metric. This is the radial component of the metric. And this is the angular contribution of the metric. here in the right, here this d omega is just the solid angle infinitesimal line element. You know, the solid angle is when you work with the spherical coordinates, when you are working in 4 space-time dimensions. One dimension is time, the other dimension is the radius, and you're going to have two angles associated with a sphere, with a 2-dimensional sphere. So the solid angle, you know, the infinitesimal solid angle square is given in terms of the azimuthal angle and the theta angle by this formula. So what I'm going to do is I'm going to replace everywhere in this formula, in this equation, in this metric, I'm going to replace r for the absolute value of the magnitude R. Okay? So I'm going to have this metric. What I'm going to do is I'm going to replace R for its absolute value, and this is what I get. Here, of course, when you take the square of the absolute value of R, it's basically the same as R squared. There's really no difference between R squared and the magnitude of R squared. But I just write it like this, you know, to remind you that what I'm doing is I'm taking the absolute values of R. Now you will say, but why do I do that when we know that the radius is a positive number? So this is absurd. This is redundant to do that. But you will see in a minute that it's not. Okay. Okay. So why am I using the modulus R? Okay. So first of all, when you change coordinates from Cartesians to spherical coordinates, you know that the radius is given by the square root of x squared plus y squared plus z squared. And remember, when you take a square root, you always have to take into account the plus and minus sign in front of the square root. Okay, so this to begin with. Second of all, have you taken classical mechanics? If you take classical mechanics, you are familiar with the Laplace operator. So I'm going to write down what the Laplace operator is. There's a fundamental difference between 1 over r and 1 over the magnitude of r. Okay? So I'm just going to plot here on the blackboard. When you plot the function f of r equals to r, you know, so this is this is what the function looks like. Okay? This is the 0. Okay, and this is r. Okay, so this is a straight line. Now, if you want to plot f equals the magnitude of r, if you take the absolute value of r, what you're going to get is something that looks like this. You're going to have, in the positive region, you're going to have something that looks like this. But in the negative region, when you take the absolute value, you're going to have something that looks like this. Okay? So this is the plot of the function, the absolute value. Okay? Now, what happens when you take the derivative? You know, the derivative of this function, you know, it has slope equal to 1. So we know that the derivative is just going to be 1 because it has a slope equal to 1. But here, you take the slope of this curve, you're going to have a discontinuity. You're going to see that for positive values of r, the slope is going to give you a 1. Okay. For negative values of r, the slope is negative, so you're going to have something that is negative. And then at 0, you're going to have a discontinuity because the tangent is discontinuous in the origin, right? You're going to have a discontinuity because the slope jumps from 1 to minus 1. So there has been a jump of 2 from 1 to minus 1. So what you do is, by convention, you take the slope at the origin to be given by the arithmetic mean between 1 and negative 1. So the arithmetic mean between 1 and negative 1 is 0. Okay? So you take 0 here. Okay, so this function over here, this function is called the sine function. Have you heard about the sine function? Okay, the sine function. Are you familiar with the sine function? Okay, the sine function is a function which is equal to 1 for positive values, negative 1 for negative values, and 0 when the function is 0. Okay, this is called the step function. Is this the Heaviside step function? Because there is okay. So this is also called the step function, where when the values are 1 for positive values, the values are -1 for negative values, and the function is 0 when r equals to 0. Okay. So now what happens if I take? Okay, remember this is I have taken the first derivative. The first derivative of the modulus is something that looks like this. There's a discontinuity, and it's going to give me the step function. What happens if I take a second derivative? Okay, the second derivative of the step function is something that many of you are familiar with, and this is the Dirac delta function. Because remember, the Dirac delta function is a function that is infinity at 0 and is 0 everywhere except at the origin. Okay, the Dirac delta is really not a function; it's a distribution. So to be mathematically correct, the Dirac function is not a function; it's really a distribution, which is 0 everywhere and is infinite at the origin. Okay. So what happens when you take the derivative of this step function? You're going to see that the step function is constant here, so the derivative is 0. The derivative here is 0, but at the origin there is a jump. Okay, and you're going to see that the slope is infinite. There's going to be a jump of the slope is going to be infinite. So the derivative of the sine function is going to be a delta function. Okay, this is very, very important. Okay, so to summarize, okay, I have a function r. Okay, when I take the first derivative, okay, I'm going to get I have the step function or the sine function, and then when I take another derivative, okay, I'm going to have a delta function. Okay, is this clear? This is very, very important, because remember, the curvature in general relativity is given in terms of the second derivative of the metric. So you're going to see that when I have a metric here that involves the modulus of r, when I take second derivatives, I'm going to pick up a delta function. And why is this important? Because here, remember, if you evaluate the scalar curvature for this metric, the scalar curvature is going to be 0. The Ricci tensor associated with the Schwarzschild solution is 0. The curvature tensor is not 0. The curvature tensor has 4 entries. So the curvature tensor associated with the Schwarzschild metric is not 0. But the Ricci tensor, when you take the trace of the Riemann tensor, you're going to have 0. And the scalar curvature, you take another trace, is absolutely 0. So remember, the Ricci tensor and the scalar curvature associated with the Schwarzschild metric is 0. But when you include the modulus here, you're going to pick up a delta function, which is what we want. Okay? And also another interesting thing is the following. By using this absolute value of r, I can perform an analytic continuation from positive values of r to negative values of r. Here, if you want to have an analytical continuation to negative values of r, you can do it, but in order to do that, you also have to switch the signs of the mass. Because if you replace r for negative r, in order to maintain the invariance of this metric, you have to flip the signs of the mass. Because if you don't do that, you're going to have a naked singularity in the origin. But here, you can switch the values of r and negative r and nothing happens. You can do that without having to flip the signs of the mass. Okay? Okay, so this is what I say here. Okay, so let me continue. Okay, so now here I have the sine function that I wrote here. So the sine function is 1 for positive values. It's -1 for negative values. And when the function is 0, the sine function is 0. And another relative point to say is that the R can also be written in terms of the modulus times the sign. So for when I have a positive function, the sign is 1, and I get obviously the obvious result. And when I have a negative value, the sign changes sign. So this relationship really is an identity. So here I can relate the magnitude of R, the sign function, with R itself. So again, the derivative of the sign function, I told you that's going to be proportional to the delta function. And you may ask, why do I have a 2 here? So the reason I have a 2 is because I have a jump from 1 to negative -1. And because I have a jump of 2, I'm going to have a multiple of 2 here. Okay? And then when you take the second derivative, remember when you evaluate the expression for the scalar curvature, because I'm going to have second derivative, I'm going to have, at the end of the day, the value I get for the scalar curvature is going to be given by the mass of the black hole, of the point mass, the Newtonian constant, and I'm going to have this expression over here. You know, notice that in general relativity, in the units I use, G times M has the units of length, you know, and delta, the delta function has units of 1 over distance. So this expression over here has units of 1 over length squared. Okay, so this is a true scalar curvature. Okay, so now if you evaluate like I said before, the scalar curvature for the Schwarzschild solution, you're going to get identically 0. Okay. So let's suppose I take the Einstein-Hilbert action. If you plug in the solution for the Schwarzschild solution here, the scalar curvature is 0. So the action will be identically 0. But now, because I have a delta function here, due to this modulus, what I'm going to have is that the Einstein-Hilbert action associated to this modification of the Schwarzschild metric is no longer going to be 0, because the scalar curvature that I get is not 0 because it has a delta function. Okay? So what we're going to do now is we're going to evaluate this integral for the modified Schwarzschild solution. Yeah. Okay, so what do I mean by Euclidean Einstein-Hilbert action? So what happens is that in general relativity, since after all I can do this. Here, you have a plus sign here, you have a plus sign here, but notice that the temporal contribution has a negative sign. Okay, so this is when you say that when you have a Lorentzian signature, because when you work with space-time, the contribution of the temporal contribution compared to the spatial contribution has a negative sign if you choose a Lorentzian metric. So what happens if you replace t for I times t, where I is the imaginary unit? When you square the I, you're going to have a negative sign, so you're going to Euclideanize the metric. So this is what we mean by Euclidean rotation, when we rotate the time by it, okay? So the t square will become minus t square. So here, when you take the measure, the square root of the minus determinant, you're going to pick up a factor of I. And then, I don't have time to explain how Hawking derived the temperature of a black hole. You see, in order to derive the temperature of a black hole, you have to look at the work of Unruth. You know, Unruth is a person who showed that the vacuum in quantum field theory is observer dependent. You know, you have an observer that is accelerating with respect to a vacuum. In other words, suppose you have two observers. One observer observes the vacuum of a quantum field theory. If you have another observer that is accelerating with respect to the original observer, the accelerating observer is not going to see the vacuum. The accelerating observer is going to see the vacuum populated by a radiation of photons. He's going to see a thermal distribution of photons, and the temperature of that distribution is going to be related to the acceleration. Okay, so the inverse Hawking temperature, remember here I'm taking the Boltzmann constant to unity. So the inverse Hawking temperature is going to be given by 8 pi times Gm, which is the length of a circle obtained from a compactification of the Euclidean time in thermal field theory. Okay, so when you do a Euclidean thermal field theory, you compactify your imaginary time, and the length of that circle is going to be related to the inverse Hawking temperature. So what I'm going to do is that at the end, when I want to evaluate the Euclideanized version of the Einstein-Hilbert action, it's going to be given by this integral. Okay, you have a factor of minus I here due to this weak rotation of my metric. Now, since I'm going to compactify my thermal interval, my temporal interval is going to be compactified. So I still have it due to the periodic thermal time. Still having an infinite value for my upper limit, I'm going to compactify along the length of this thermal circle. Okay, so remember, beta H is inverse temperature, and the inverse of temperature is like the inverse of energy. It's like a length. Okay, so here I have the inverse Hawking temperature over here. Here I'm going to integrate over my radial directions. Due to the spherical symmetry, I have an integration over my solid angle, which is 4 pi, and I'm going to integrate between 0 and infinity of my radius. Okay? So remember, my curvature now has a delta function. Okay? So, in order to integrate the delta function, so some of you remember that the delta function is a symmetric function of the argument. The delta function is symmetric. It's a symmetric function. So meaning that when you replace r from negative r, you get the same function. So due to the symmetry of my delta function, when I integrate between 0 to infinity, I can integrate from minus infinity to infinity, and of course due to the symmetry of the integral, I need to include a factor of 1/2 here. So the integral of this delta function between 0 and infinity is actually 1/2. Okay? So notice that it's the key presence of the magnitude in my metric which allows an analytical continuation. Okay? Remember, I can perform an analytic continuation of this integral because I was using the absolute value of r in my metric solution. Okay, so given the expression of the inverse Hawking temperature, given the expression for my curvature, and this integration over here, I know what this is, I know what the curvature is, and I can do this integral. So after you evaluate this integral, what do you get? You're going to get a numerical expression, okay, and you're going to get that the magnitude of that Euclidean Einstein-Hilbert action associated to that scalar curvature that had a delta function. When you do the integral, you do the algebra, what do you get? You're going to get an expression which is precisely equal to the black hole entropy. Okay, so let me just go slowly here. The answer you get after you do all that integral, taking into account that the curvature scalar has a delta function, this is the answer you get. Okay? So you're going to get an expression that is given by 1/4 of the ratio of the area of the black hole horizon. Remember, let me just watch afterwards since I have time. The black hole horizon happens when the temporal component of the metric is 0. When is this value equal to 0? This value equals to 0 when the radius equals to 2gm. 2gm is the horizon radius for the black hole. It's the event horizon radius. So when r equals to 2gm, this expression is 0, so this is when you reach the horizon of the black hole. Okay. So you can rewrite this expression here as 4 pi 2gm. Okay, remember this is the radius of the horizon. 4 pi r squared, this is the area of the horizon. This is 1/4, which is essential. The 1/4 appears, that is essential. And then remember, G can be related to the Planck length square. Okay? So let me just write here in the board what the Planck length is in terms of the fundamental constant. The Planck length is associated with a black hole whose mass is equal to the Planck mass. Another way of saying is the Planck length is associated when you have when the Schwarzschild radius is of the order of the quantum wavelength of the particle. But anyway, I'm not going to, because you have to take quantum field theory, but essentially in physics there's some fundamental constants. So the Planck length, okay, Planck, in 4 dimensions, okay, is given by this expression in terms of units. Okay, this is okay, and you obtain the Planck length when you have a black hole, whose event horizon radius is of the order of the quantum wavelength of the particle. Okay, so if you have a particle of mass m, the quantum wavelength associated with that mass is given by this formula. Okay, and if this quantum wavelength is of the same order as the Schwarzschild horizon associated to that particle, then in this case, let's do it correctly. From this formula here, you can obtain the Planck length, and the Planck length in 4 dimensions is given by this expression here. Okay, so the Planck length square, okay, is actually h c square times g. And remember, because at the beginning of the lecture, I used the units that h bar was equal to 1 and c was equal to 1. What happens here is that g here really, if you set h bar equals to 1 and c equals to 1, it happens that g is equal to the square of the Planck length. So the black hole entropy really is given in terms of the ratio between the area of the event horizon, the area of that sphere, in Planck units. So you want to compare the area of that horizon, you divide by the square of the Planck length. So this is how big is the area in terms of the Planck units. And that is a measure of the entropy, once you include the factor of 1/4. Now let's suppose that you want to reinstate the numerical constants that I set to unity. Remember, I set the h bar equals to 1, c equals to 1, and the Boltzmann constant equals to 1. If you want to reinstate the units, to give you an idea why this is very, very important, when you reinstate all the units, what you're going to get, let's hope this writes. Yes. So you're going to have that the entropy, okay, there's going to be a factor of 1/4. And remember, the entropy has units of the Boltzmann constant. The Boltzmann constant has units of entropy. So you're going to have a factor of the Boltzmann constant here in front. Okay, and then on the right-hand side, you're going to have an area, and then you're going to have a Planck length square. Okay, but remember, the Planck length, I told you, in 4 dimensions is equal to h bar g divided by c cubed. Okay, so when you bring all these constants, when you arrange everything, you're going to have, okay, I'm going to write 1/4 here to tell you that the entropy is always proportional to 1/4 of the area. Okay, so you're going to have the Boltzmann constant over here. The speed of light to the cube power is going to appear on the top. You're going to have the area here. And in the denominator, you're going to have the Planck constant and the Newtonian constant. Okay? So here, you're going to see that all the fundamental constants in physics appear, because you're going to have the Boltzmann constant here, you're going to have the speed of light here, you're going to have the Planck constant here, and you're going to have the Newtonian constant here. So this is why black holes are very important, because when you include quantum effects, it contains all the fundamental constants in physics. Now, some of you may ask, what happens if I set h bar equals to 0 here? Let's suppose you want to take the classical limit of this formula. You're going to get something which is infinite. It will blow up. So you cannot really take the classical limit, because this expression is inherently quantum. But notice that this entropy is huge, because h bar is a very small number. C is a very large number, so the entropy associated with the black hole is enormous. Okay, so to summarize, what I have done, I have taken the Schwarzschild metric. Okay, now the most important thing is can I erase this? Okay, why is the modulus so important? Okay, why is the modulus so important? Okay, if you take the Laplacian operator in the spherical coordinates, don't worry too much. Let's suppose you're working in 3 flat space dimension, and you want to evaluate the Laplacian of a function. Okay? Let's suppose I want to take the Laplacian of 1 over r in 4 dimensions. Okay? So you can find this in any book you want. In 4 dimensions, in 3 spatial dimensions, and if the space is flat, when I take this Laplacian, I'm going to have 1 over r squared here. Okay, I'm going to have the derivative with respect to r, parentheses, and I'm going to have r squared, and I have the derivative with respect to r of the function I want to take is 1 over r. Okay? Okay, so when you 1 over r. Okay, remember you are in 3 spatial dimensions in the flat space. Okay, it's 1 over r squared. You have to have 2 derivatives. You have one derivative here, and the second derivative appears here. Okay, and and if you want to make sure that you have the right units, remember you have an r squared here, and you have an r squared here. So the units are correct. The dimensions are correct. Okay, so when you evaluate this expression, remember when you take the derivative of 1 over r, you get minus 1 over r squared, right? So you have a minus, okay, r squared. Here you have 1 over r squared, right? And I put the minus outside. So what happens when you do that is that you have an r squared here, and an r squared here, so they cancel, and the derivative of a constant is 0. Okay. So this is trivially 0. But what happens when you take the derivative of 1 over the modulus? When you do that, 1 over the modulus, okay, I'm going to write everything as before. Derivative of 1 over the modulus. Okay, so when you do that, you're going to have minus 1 over r squared, derivative of r squared, 1 over r squared, but don't forget the step function, the sine function. Because remember, when you take the derivative, when you use the rule of the differentiation, you're going to have, actually, in order to be rigorous, this square, and then you're going to have this sine function, the sine function here. Because remember, the derivative of the sine function, which is the step function, is going to give you, of the modulus, I'm sorry. I have to take the derivative of the modulus. Okay, the derivative of the modulus, I'm sorry. Okay, so what I'm going to get here is 1 over r squared derivative. Okay, remember this is going to cancel with that, And the derivative of the modulus is going to give me the sine function, right? The sine function. Okay. And remember, the derivative of the sine function is no longer 0. You are going to pick up a delta function, and this is when you pick up the delta function. So notice the fundamental difference when you take the Laplacian of 1 over r compared to the Laplacian of 1 over the modulus of r. You're going to pick up an essential delta function. So this is basically why the delta function is going to appear when you evaluate the curvature, a very intuitive picture. And why do you want, and why this is what you want? Because remember the Poisson equation in ordinary Newtonian mechanics, the Laplacian of a gravitational potential is going to give you on the right hand side, it's going to give you the mass density. Remember the Poisson equation, the Laplacian of a potential is related to the mass density distribution in the right hand side. So if you don't have any mass in the right hand side, the Laplacian will be 0. So this is why the gravitational potential, if you want to be rigorous, the gravitational potential, if you want to be rigorous, associated with a mass m, if you want to be rigorous, you should use the absolute value of r. So when you take the Laplacian, you're going to get the delta function, because when you have a point mass, the mass density associated with the point mass will have a delta function. Okay? I hope this is clear. This is probably the, I guess one of the most important things you will get out of this lecture. Okay? Can I continue? Yeah. You see, many books erroneously say that the Laplacian of 1 over r is the delta function. That is incorrect. It's the Laplacian of the 1 over the modulus. And if you look at the quantum mechanics book by Griffiths, I think they make the same mistake. I noticed that in some of the, okay. Can I continue? Okay. So now the question is, how did Gibbons and Hawking and George evaluated the entropy of a black hole for the Schwarzschild solution? You see, Gibbons, Hawking, and York modify the Einstein-Hilbert action by including the boundary term. So remember, the scalar curvature associated with the Schwarzschild solution is identically 0. So obviously, the Einstein-Hilbert action associated with the Schwarzschild solution is trivially 0. So what Hawking, Gibbons, and York did, they include the boundary term over here, where now you integrate over the boundary of your manifold. Over here you have the square root of the determinant of the induced 3 metric. Capital K is the trace of the extrinsic curvature, and you integrate it over the 3-dimensional boundary. Why do you introduce a boundary? And so the reason Gibbons, Hawking, and York introduce a boundary term is the following. It's actually more subtle. You see the curvature, the way Einstein, when he was working with Riemannian curvature, the curvature is in general given in terms of 2 derivatives of the metric. So what happens is that they wanted to work, Gibbons and Hawking and York wanted to work with an action that only depends on the first derivative of the metric, instead of a second derivative of the metric. So remember, in relativity, there is something called the Palatini formulation of general relativity, where you treat the metric and the connection to be independent of each other. Because usually the connection is given in terms of first derivative of the metric. But in the Palatini formulation of general relativity, you treat the connection and the metric to be independent entities. So it happens that when you want to do a path integral formulation, there is something called the composition property of the path integral. So you have to work with a theory that involves first derivatives, not second derivatives. So what happens is that, so when you work with a theory that has only first derivatives, it happens that the variation of the metric at the boundary is 0, but a variation of the first derivative of the metric on the boundary is not 0. So what happens when you do that, you are going to modify the Einstein field equations, because you are going to introduce extra terms due to the fact that the variation of the first derivative of the metric is not zero. So in order to reproduce the Einstein field equations, you have to introduce a boundary term. You have to introduce this boundary term whose contribution is going to cancel the extra contribution you had when the first derivative of the metric, the variation is not zero. So this boundary term is necessary in order to reproduce the Einstein field equations. So when you do that, then you get up with this given Hawking-York action, which includes a boundary term. So when the curvature scalar is zero in the Schwarzschild metric, then this term is zero, and you end up having this contribution to the boundary term. And when you do that, Gibbons and Hawking showed that the Euclideanized version of this action is going to give you the black hole entropy. This is how it is done in the orthodox standard way all over the world. But what I've done here is I just forgot about these boundary terms, and I just work with a modified action, taking into account the absolute value of my radius. And in doing so, my curvature scalar curvature is not zero. I evaluate the Euclidean version of this action, and I obtain the black hole entropy. So there are two ways of doing this. You can do it the way I've done it here, or the conventional orthodox ways of doing it, which is, by introducing this boundary term. So it's interesting. Yeah.
So here, M is the...
Your manifold. The manifold.
Manifold.
Oh, I'm sorry. M is not the manifold. M is the manifold. I'm sorry. I'm sorry. By M, I mean the manifold. 4D manifold. Yes.
And what sort of the boundary actually is three dimensions?
So you introduce a three-dimensional boundary at infinity.
At infinity.
At infinity. Yeah. You assume the metric is asymptotically flat. Okay. Any questions about this? Okay, so this is the motivation of comparing the two approaches. Okay, so now what I'm going to do is I'm going to evaluate the entropy in the case when I'm working in higher dimensions. So I'm going to repeat what I had done here in higher dimensions. So it happens that the solutions of the Einstein field equations in vacuum in higher dimensions, they were found by the Italian guy Tangerlini, So the solutions I'm just going to give you the answer. What he did is that, remember, when you're working in higher dimensions, you have one dimension is your time, another dimension is r. When you're working in d dimensions, the transverse dimension, the complementary dimensions to your radius and your time, is going to give you a d minus 2 dimensional solid angle, because you're adding d minus 2 extra dimension. So you have a hypersphere of d minus 2 dimensions. In general, the horizon in higher dimensions is not necessarily spherical. It could be an ellipsoid, but anyway. So the metric is going to be, so also another thing, for the Schwarzschild solution, I have this expression over here. For the Tangerlini solution, you have something similar, where now you raise the ratio of the horizon radius relative to r, you raise it to the power of d minus 3. Because when d equals 4, 4 minus 3 is equal to 1, you recover this expression over here. Okay? So I'm going to tell you what f of r is. F of r is this complicated expression, but this expression can be written in this form: some horizon radius divided by r raised to the d minus 3 power. Okay, so I'm just going to go forward here. This is the solid angle in d minus 2 dimensions. It's given in terms of the gamma functions. And then the horizon radius is determined from the condition. Okay, so when the radius equals to the horizon radius, this expression over here becomes 0. Okay, f of r becomes 0 at the horizon. So the horizon, this is the expression for the horizon. Remember, when d equals 4, 4 minus 3 is equal to 1, this becomes 1, and you get that, you get the ordinary horizon radius of 2gm. But in higher dimensions, you get a more complicated expression. So the metric in higher dimensions, the higher dimensional version of the Schwarzschild solution in higher dimensions is given by this expression over here, where you have now this ratio of a horizon raised to the d minus 3 power. This is the temporal component of the metric. The radial component is the inverse of that. You're going to have a radius square, and then you're going to have this solid angle raised to this power. Remember, you have an r square here because you have an element of length square over here. Okay, yes.
Yeah. So in the equation 12.
Yeah.
Yeah.
This is the solid angle. When imagine you have a sphere, a hypersphere of radius 1.
Yeah. And
this is the solid angle.
Yeah. And maybe you might have some. So I understand. So is it?
This is divided.
Yeah. Those are the constants, right?
Here I'm dividing by the gamma function.
Yeah, that's a constant.
Yes.
And you need some coordinates. Or
yeah. Well, I'm giving you this is the integrated solid angle over the whole hypersphere.
Right.
Yes. This is the differential element, and this is the integrated. Yes. Yeah, you're right. Not to be rigorous. Yeah. This should be the solid angle, the total solid angle of a d minus 2 dimensional hypersphere. Yeah. Here, did I write it here? Yeah. Okay, the total solid angle. I forgot to include the word total. Okay. So now what I'm going to do, here, you see you have an r over here, you have an r over here. So what I'm going to do is I'm going to, again, if you evaluate the scalar curvature associated to this metric, if you evaluate the Ricci tensor associated to the metric, you're going to get identically 0. However, when I replace r for the absolute value of r, you are not going to get 0. Okay, this is the modification I'm going to do. Okay, r. So now, due to this, this behavior that I showed here, it happens that when I replace the r for its modulus, when I evaluate the scalar curvature, you're not going to get 0. You're going to get this is the algebra. When you do the algebra, blah blah blah. Remember, the derivative of the sine function is 2. You have all of these expressions. When you do all the algebra, at the end of the day, this is what you get. The scalar curvature in d dimensions is going to be given by this expression over here. Here, I mean the total solid angle. Okay, I have a delta function here. I have this expression raised to this power. Because remember, the units here, all the units change. When you're in higher dimensions, the units of the Newtonian constant is the Newtonian constant in d dimensions has units of a length raised to the power of d minus 2. Okay, remember, this is the Newtonian constant in d dimension that has different units than in 4 dimensions. So then you can rewrite this in terms of the horizon in this expression. Okay, so this is the scalar curvature in higher dimensions due to modifications of the Tangerlini metric by replacing r for the modulus of r. So this is what you get. Okay? So now I'm going to do the same thing. I'm going to evaluate my Einstein-Hilbert action in higher dimensions, taking into account that now the temperature of a d-dimensional Schwarzschild black hole, the temperature now, the inverse temperature is given by this expression over here. Where now, this is the horizon radius associated to the high-dimensional black hole. Remember, the horizon radius is more complicated. It's given by this expression over here. Okay? So this is the inverse Hawking temperature. So now the non-trivial Euclidean Einstein-Hilbert action in d dimension is given by this integral. Okay, where now this is the inverse Hawking temperature in d dimension. So when I plug in this value of r given by this expression over here, when I do the algebra, what do I get? When I do the algebra, I get, this is the answer I get. Okay? So what do I get over here? I have the famous 1/4, okay, and this is the area of a hyperspherical horizon. Remember, when I'm working in d dimensions, these are my two transverse directions to r and t. So this is the area of a hyperspherical horizon. This is the total area of a hyperspherical horizon divided by 4, and then I have to divide by the gravitational constant in d dimensions. So this is the answer you get. So it's really interesting that you get precisely, again, the 1/4. The entropy always has this 1/4 value of a horizon area in the right units. Okay? So if you want to rewrite this in terms of G and N on the horizon and the solid angle, this is the expression you get. So this is actually very curious that you also get the factor of a quarter here. And the reason you get this factor of a quarter is it had to do, remember when I took the derivative of that step function? The derivative was proportional to the delta function, but they had a key factor of 2, because there was a jump from 1 to -1. So that factor of 2 in the derivative of the step function was essential. And the fact that also, in order to integrate the radial integral between 0 to -infinity, due to the symmetry of the delta function, is equal to 1/2 the integral from -infinity to infinity. So those factors of 1/2, 2 are essential, and you always get you recover this factor of 1/4. Okay. So now you may think, okay, this is all very nice, but now I want to learn a little bit more about the point mass. Okay, I have a point mass at the origin that gives birth to this entropy when I do the Euclidean action. So I want to learn a little bit more. What is the nature of this mass distribution that I have at the origin? Okay. So how much time do I have? Yeah.
5 minutes.
Okay. So if you want to find what is the mass density associated, remember I have a metric. I evaluate the Einstein tensor. I do all the algebra. Then at the end of the day, I have to get something which is not 0, because I need to get something in the right-hand side that gives me the stress energy tensor. Okay? So when you do the algebra, it turns out that I'm just going to give you the answer. At the end of the day, okay, that in d dimensions, in general, the energy density is going to be given by the mass, of the point mass. You have a delta function. You have a solid angle in d minus 2 dimension. You have this expression. You're going to have a radial pressure. The radial pressure is going to be proportional to the density, but it has a negative sign because of course you want to have something which is self-gravitating. Okay. So what I'm going to have really, imagine you have a spherical droplet, a fluid droplet, like a balloon of water, which is self-gravitating. Okay? So if the balloon of water is self-gravitating, it has a certain mass density, but because it's self-gravitating, the pressure has to point radially inwards, because it will tend to collapse, right? So this is why you have a negative sign here, because the radial pressure is the opposite. It has to point inwards, okay? And then the values of the tangential pressure, the pressure along the hyperspherical directions, along the angles, is going to be given again by an expression which is proportional to the density, in such a way that the trace of your stress energy tensor, the trace of the energy tensor has to be is given by this expression. But in order to make sure that you did the calculations correctly, the trace of the stress energy tensor has to be related. This is the trace of the stress energy tensor. It has to be related to the scalar curvature. Because remember, when you take the trace of the Einstein field equations, the trace of this equation here will give you a quantity proportional to the scalar curvature. On the right-hand side, if you take the trace of the stress energy tensor, so you're going to find a relationship between the scalar curvature and the trace of the stress energy tensor. So you obtain this relationship between the trace of the stress energy tensor and the scalar curvature. Remember, the scalar curvature had a delta function. So at the end of the day, to make sure you did the calculation correctly, you better make sure that the trace of the stress energy tensor is going to give you by this expression. The reason you have a negative sign here is due to the signature. That's why you have a negative sign here. Okay, so now the main point of all of this is that if you look at these equations over here, you're going to see that all these solutions, 25A and 25B, satisfy the strong energy conditions, which is given by this formula. When you take the density and you sum over all the pressure components, you obtain something which is greater or equal to 0 only when the dimension is equal to 4 or 5. And the weak energy conditions are satisfied only when the dimension equals to 4. So the space-time dimension that you and I observe is very, very special, because it is the only dimension over all the other dimensions that satisfies the strong and the weak energy conditions. So the space-time dimensions that you and I observe are singled out from all the others if and only if the strong and weak energy conditions are satisfied. Because remember, in string theory, when you look at the bosonic string, if you want to evaluate, you end up with so-called quantum conformal anomalies, except in 26 dimensions. So 26 dimensions is singled out in bosonic string theory when you want to cancel the so-called quantum anomalies, the conformal quantum anomalies. And if you work with the superstring, when you include supersymmetry, if you want to cancel the superconformal quantum anomaly, you single out 10 as your critical dimension. So in string theory, 10 is the critical dimension of the superstring, and 26 is the critical dimension of the bosonic string. But you have to do a quantum calculation in order to do that. But here, it's interesting that you can single out the space-time dimension that you and I live in without having to invoke string theory or quantum field theory. So it's interesting that by doing this simple calculation, actually what I've done is all classical. Of course, the entropy, you have to include the quantum effects, because the Hawking temperature really is a quantum result. But here it's interesting that you can single out the space-time dimension you and I live in by invoking the strong and weak energy conditions. And then finally, you can repeat all these calculations for the Reissner-Nordstrom black hole, which includes a charge, and also for a rotating charged black hole, which is the Kerr-Newman solution. So since actually Eckhart printed a bunch of, so all of you got a copy of the print? Ah, okay, good. So you can look out about how to derive the black hole entropy for a charged rotating Kerr-Newman black hole. And before I finish, when you have time later on, I recommend you look at the YouTube lectures by Witten. You see Witten in the fall of 2022. He gave a very nice course on black holes, black hole entropy, Foy-Neumann algebra, quantum information theory, which I really recommend. These are 22 lectures by Witten, and they are on YouTube, and I really recommend them. Of course, they are very advanced, but you have to see, you get a chance to see Witten in person. So, he's a living legend. So I really recommend him, because actually he does everything on the blackboard. He doesn't use slides, so he uses pencil and blackboard. So it's so I really recommend it. Maybe, of course, it's a little bit advanced for you, but look at the YouTube lectures by Witten, especially if you want to learn a little bit about the connection between Foy-Neumann entropy, quantum information theory, black holes, entropy, and everything. I do recommend it. So like I say, you have a lot of time in the future, so I really recommend it. Okay? So thank you very much. Thank you.